Hi, and welcome to my pizzeria. While you are here to listen to the podcast, maybe you have a slice, eh? This podcast is going to be all about intermolecular forces. Because after all, we've talked about gases a little bit. We also want to delve into solids and liquids. And after all, what is it that makes a solid a solid? Why is a gas, even though it's a certain temperature, a gas, while other things at the same temperature, well, they're a liquid or a solid? And really it all comes down to intermolecular forces. This is a table that describes all of the intermolecular forces. It also lists an energy range. So how much energy? And you can see that as a force of attraction. Notice these numbers at the top. They're pretty large numbers. Those are strong intermolecular attractions. Then look way down here at the bottom. These attractions are quite weak. So the numbers that you're seeing give you some kind of idea of how strong that force of attraction is. I'm just going to touch on a couple of them, and I'm going to give you a chart in a minute that helps explain it. Now, I will post this so that y'all can see it. This exact picture right here, I will post so that y'all can see it. Don't worry about writing everything down. But just kind of get an idea of how this flows. Ion-ion interactions are where something is plus 2 and minus 2, plus 1 and minus 1. They have a full-on whole number charge. That's a lot of attraction, and as you can see, it's pretty strong. Even metallic things have a very strong pull towards electrons. It has a very strong attraction between protons and electrons, between protons of, say, one iron atom and the electrons that live next door. As we get down into this blue section down here, realize that there are a whole host of intermolecular forces you could have. You could have the force between an ion, like right here, sodium, a sodium ion in water, and we just call that dissolving. The water is going to be attracted to the sodium ion. We have a hydrogen bond. A hydrogen bond is very, very particular. A hydrogen bond is when a hydrogen is bonded to a nitrogen, an oxygen, or a fluorine, thus making the hydrogen have a pretty positive charge. That hydrogen is then attracted to a fluorine, oxygen, or nitrogen on another molecule. So we will say that hydrogen bonds have to have Fon, F-O-N, Fon, on both sides of the hydrogen. The hydrogen has to be covalently bonded to a fluorine, oxygen, or nitrogen on one molecule, and then has to be attracted to a totally different fluorine, oxygen, or nitrogen on another molecule. A dipole-dipole force is just where you have two molecules that have positive, negative ends. And those positive and negative ends are attracted to each other. So really, in a way, a hydrogen bond is a type of dipole-dipole force. It's just a very specific type of dipole-dipole force. Here is a very good description of the difference between a hydrogen bond and a dipole-dipole. On the left, you see this oxygen right here. It's bonded to a hydrogen. That makes this hydrogen a little bit positive. Notice how the hydrogen is attracted via the green arrow to the oxygen on another molecule. There is Fon, F-O-N, on both sides of the hydrogen. Notice all the hydrogen bonds that are drawn in green arrows have that Fon on either side of the hydrogen. Now swing over here. This is a dipole-dipole interaction. Notice that the hydrogen on water is attracted to the chlorine on that molecule right there, the CH2Cl2. This would not be a hydrogen bond. This would be a dipole dipole. The arrows are showing the direction of polarity. So the tip of the arrow is a negative side of the molecule. The other end of the line is the positive side of the molecule. So you've got a hydrogen on the water being attracted to the chlorine on the CH2Cl2. That's not a hydrogen bond because it doesn't have FON on both sides of the hydrogen. Ion-induced and dipole-induced dipole, that's just a fancy way of saying that ions can make something polar. The positive end of an ion can attract the electrons that are circling around a molecule, causing, for an instance, a brief attraction. The one I want to worry about is this one at the bottom, London dispersion forces. Let's not call them van der Waals forces. Let's call them LDF. And LDF is where you have two totally non-polar molecules. They have nothing to do with each other. And for a brief instance, there's one molecule ends up with electrons more so on one side than another. And for a brief moment, there's a little bit of attraction. Notice the number. The hydrogen bonds, the dipole-dipoles, are way stronger than the London dispersion forces. This is a very good description that you may want to get down. How do those intermolecular forces work? And remember, intermolecular forces have everything to do with how matter behaves. Is it a solid, a liquid, or a gas? A is an example of a dipole-dipole force. And below it, you see a lot of those molecules all interacting with each other, some repelling and some attracting each other. And it is that total force, once you take away the repulsions and add the attractions, all of it together, that helps decide what state of matter a substance is at a given temperature. So London dispersion forces are just like a hydrogen bond, but they're very, very fleeting. So these are relatively weak forces, weak in that they don't last for very long, between nonpolar molecules and also noble gases. So things that will never ever be polar, argon, that C8H18 is octane, a component found in gasoline. They're caused when, out of the blue, you get this instantaneous dipole. All the electrons are behaving themselves, and then for a brief instant, the electrons end up more on one side of the molecule than the other. One word we use to describe how easy it is to form this distorted cloud is called a polarizability of an atom. So in the top right-hand corner, you see molecule A and molecule B. Notice both hydrogens, and they are totally nonpolar. There is not one that is more electronegative than the other. Down below it, you see molecule A and molecule B. Molecule A has distorted itself, and now the electrons are more on the left-hand side over here, and there's less electrons on the right-hand side over here. This is called a polarization event or a instantaneous dipole. And then if we just click down one more time, here we are, and the fact that the molecule on the left is polar for an instant has induced the molecule on the right to follow suit. The electrons on the molecule on the right are going to be attracted to the positive end of the polar molecule on the left. And we just call that instantaneous dipole. So you need to know just these properties of a liquid. Know what surface tension is, know what capillary action is, and know what viscosity is. Right? So just add them to your vocabulary words to look up. And I'll give you a couple examples to help you along. Surface tension is the fact that water would rather stick to itself, right? So what is surface tension? Well, put a drop of water down on a surface and it forms a bead. That's because the water molecules are very attracted to each other. Sometimes we want to break that. Inside your lungs, you have molecules called surfactants, and we use those same surfactants in cleaning materials like detergents. Those surfactants actually break the surface tension, allowing that water to spread out. Capillary action is when water molecules stick to each other so much that when they start to go up, say, a paper towel or up a tree trunk, they will drag other water molecules along with it. So the water will stick to the wooden tube inside the tree, and they will also stick to each other. Viscosity is important because you can have a liquid that's super viscous. So molasses, way viscous. Motor oil can be viscous, can be not so viscous. It really is a function of temperature. So if you ever change your own oil, or if you ever want to learn about oil, you can go into an auto parts store and notice that there are many different viscosities based on how hot or cold it gets in your environment, and also the specific needs of your engine. When we look at solids, and especially crystalline solids, it's helpful to realize that we can identify the crystalline structures and we can analyze the crystalline structures using this horrible equation called the Bragg equation. So look at this here. Isn't that horrible? Yeah, we'll never ever use that equation. But basically what it says is that if you shoot X-rays at something, the way the X-rays bounce off of it tells you something about the design of the molecule. This is a famous molecule of DNA in the top. This is an X-ray crystallography shot of it. The woman in the lower left, Rosalind Franklin, took those pictures of DNA, and Watson and Crick in the 1950s used those pictures to help them decipher the structure of DNA. So by shooting the X-rays at it and using the Bragg equation and a lot of trigonometry, you can actually sit and analyze crystals. And that's true for DNA, but also true for certain drugs, right? If you get a drug out of a plant and you want to know what the structure is like, you can do X-ray crystallography, and by analyzing those, you can know the structure of that molecule. So vapor pressure is exactly what it says. And obviously, the easier it is for a molecule to turn into a vapor, then the more vapor molecules you're going to have. The harder it is, the less vapor pressure. So let's think of something that's really hard to turn into a vapor. Rock! That's right, rock. Why? Because the forces holding it together are so super strong. What's something else? Asphalt, right? Asphalt. And asphalt doesn't have a lot of forces holding it together, but you know what it has? Really honking huge molecules. We could talk about molecules that are several thousand or million grams per mole, right? Because these molecules are just long chains of repeating structures. And it's going to take a lot of energy to take that molecule and make it knock loose of the other molecules and become a vapor. So things that evaporate easily we call volatile. And so volatile liquids, since they evaporate easily, they're going to have higher vapor pressure. A melting point tells us something about a molecule. Let's imagine a molecule. Will this one do? No. How about this one? Y'all are picky. Okay, how about this one? Okay, this one we can go with. If this thing has a high melting point, that tells us something about it. It has high intermolecular forces, or it's a really big molecule. That's what it tells us. If it has a low melting point, it tells us it has low intermolecular forces or is tiny. Either one of those, we can not only consider melting point, but also boiling point. Same idea. The higher the boiling point, obviously the higher the intermolecular forces are. And we define boiling point as the temperature at which the vapor pressure of the liquid equals the ambient pressure. So what's just the pressure around it? If you raise the pressure, well then obviously there's more ambient pressure. You're going to have to make the vapor pressure higher. And since you can't really just change the molecule or add more molecule because it's still the same molecule, the only way to jack up the vapor pressure is to increase the temperature. So the net effect of that is the higher the surrounding pressure, the higher the boiling point is going to have to be. I'm sure you've seen this graph before, and it's just a graph showing the change of phase of ice from negative 20 to 0 as it warms up, and then the ice and water melting, which is all about breaking those intermolecular forces, and then the water heating up, and that's all about speeding up molecules, and then the water and steam, which is the molecules breaking those intermolecular forces, and then the steam getting warmer just means, yes, that those molecules are heating up again. The bottom axis down here, just by the way, that's heat being added. So a long time you're adding heat to the system.